Okay, we are into the final subtopic of managing resources and the final subtopic of the year, which is materials. And we'll do this over 3 parts. We'll look at polymers, then we'll look at metals, and then we will look at recycling in part C. So let's get into polymers. So this first part of polymers, it actually revises a lot of stuff we did in stage 1. I've actually pulled some of these diagrams and some of this stuff out of the stage 1 notes from last year. Hopefully I'll go through it well enough, but if you need to, you could go back and revise that video. It also revises a lot of the stuff we did on inorganic chemistry, particularly about addition reactions, which was often like the test for bromine, so adding bromine to an alkene to get addition across the double bond to check for the presence of double bonds, or the margarine synthesis where we added hydrogen across the double bond. It's a bit of a variation on that. It's about the condensation reactions, both to produce esters and to produce amides from amines and carboxylic acids as well. So, what do we need to know about? Firstly, we need to be able to identify whether a molecule could undergo polymerization given its structural formula, and if so, the type of polymerization. So if we look at these bits in green, alkenes are able to undergo polymerization because basically if we have a series of alkenes, and here I have got using as a basis, this is, I should label that, the plastic PVC that you're probably familiar with from water pipes and lots of other related things. So this structure here is PVC, which stands for polyvinyl chloride. That's its common name, not its systematic name. We don't tend to have so much systematic names for polymers, but as I said, it's made from an alkene. That's its monomer. So we're talking about go back to my pointer, these are the monomers that you would use to make PVC, and they contain an alkene, so that's why that they can undergo this reaction. And in a sense, remember, all the chemical bond is a shared pair of electrons, and this one of these 2 double bonds moves from here to in between the next 2 carbons, and from here to the next 2 carbons, and that gives you that continuous polymer structure. So our monomer here, if we were to name that 2 carbons, so it's eth, it's got a carbon-carbon double bond, ethene, but it's also got a chloro group. Now we don't need to know how to name these at the moment, but we would call that chloroethene, which sort of probably makes sense from what you know about naming chemicals. I haven't written that down because you don't really need to know that. But how do we know that it will form? It's got a carbon-carbon double bond, so it can form a polymer. What type of polymer would it be? This comes up in the next point. I'm jumping ahead. It would be an addition polymer. We get addition across the carbon-carbon double bond. The next type of molecule that we need to talk about that can form a polymer is the ones that form the polyesters. So again, I probably should have written that down. This is an example here of a polyester, and you've probably heard that term before. So esters form where we have a carboxylic acid group and an alcohol group. When they react, we lose that water, so we lose those 2 hydrogens and the oxygens in yellow, and then a bond forms between that carbon and that oxygen. That's the bonds, if you like, that are formed here. And as that goes on, we basically get this continuous structure. Now, to make this structure keep building, we need to either have a diol, which is a dialcohol. So here's our diol here, the alcohol at each end, 2 alcohols, and a dicarboxylic acid. So here's our carboxylic acid at each end. And if you have these structure, they can basically just go on and on and on joining to form a really long structure, like this example here, which is dacron. Dacron is a material, I know from personal experience, it's a material that's used to make sails. but it's probably used for lots of other things as well. I think it's also used in some medical implants and that sort of thing from memory as well. Not that that's all that important. The other way that you can get a polyester form, which wouldn't be like Dacron here, is if you have a hydroxy carboxylic acid. So we have a hydroxy on one end, a carboxylic acid on the other. These could basically just go on and on joining just from a single monomer to give us a polymer. Here, if you like, we've got two monomers that are going together to make the polyester. So how do we know whether it can undergo polymerization? Does it have either the dialcohol and the dicarboxylic acid or a hydroxycarboxylic acid? What type of polymerization would this be? This would be a condensation polymer or a condensation reaction because water is released each time they join. We also get a fairly similar story with these grouped down here, which again I could probably label. These ones down here are polyamides. So amides are like the nitrogen equivalent of esters, you've probably heard me say. So now, instead of having a dialcohol with two OH groups on the end, we've got a diamine with two amine groups, plus a dicarboxylic acid again, the same as the one up above. Basically, they keep joining. Each time they join, they release water, hence condensation, water producing, to form the polyamide. Now, the other way we can get that is if we have an amino acid, and this is what happens, if you like, in nature with proteins, which has an amine group at one end and a carboxylic acid at the other. And we've already talked about these when we've done the topic on proteins and how they form from amino acids. But you can also get synthetic polymers produced in this way. Proteins are made from those 20 or 21 odd occurring natural amino acids which join together in various sequences. So again, if we have an amine group and a carboxylic acid group, we have the ability to form an amide that can form a polymer, so a long continuous chain if we either have a diamine and a dicarboxylic acid. So in this example here, we'd have this amine and this carboxylic acid. They go together to form this compound here, which is nylon. So nylon is another fairly common synthetic fabric that you've probably heard of. But we can also get this same process if we have a amino acid, which is basically a compound that contains both an amine group and a carboxylic acid group. So I think I've covered, just quickly, so I've identified a polymer as being the product of addition or condensation. Just to be clear there, addition, we have a continuous carbon backbone. So that's how we know it's addition. We have just this continuous carbon backbone. We might even write that in. So we have a continuous carbon backbone. How do we know if it's a condensation polymer? We have these basically oxygen links, if you like, or we have nitrogen links in the case of an amide. So here we have, if I use purple, no. So how do we know? We have basically, just let me move that out of the way. We have the oxygen links like so. And how do we know if it's a condensation reaction? In the case of a polyamide, then we would have the nitrogen links shown there. So if we've got nitrogen or oxygen links, it's a condensation polymer. If we've got a continuous carbon backbone, then it is a addition polymer. The other thing you need to be able to do is identify the repeating unit. I think that should be self-explanatory there. That's the bit that repeats over and over again. So I've highlighted the repeating unit there in blue, and the repeating unit for Dacron and for nylon are also highlighted there in those blue boxes. We covered that last year. That's just looking for that pattern about where the molecule repeats itself. We've also covered that with amino acids and various things. So hopefully that is fairly straightforward. So we've done the chemical reactions part of polymers. Now let's get into some of the properties of polymers and some of the issues around the use of polymers. So just following through here, the production of synthetic polymers allows the manufacture of materials with a diverse range of properties. I think we all know that we have lots and lots of different polymers in the world to do all sorts of different things. Discuss the advantages and disadvantages of synthetic polymers. So the advantages of synthetic polymers are they're generally cheap to manufacture, particularly compared to materials like timber, metal and glass. They're light, which makes them, well, generally they're very light, which makes them easy to handle and transport. And they can be made with a range of properties. Either we can make really rigid polymers, where we need objects that are quite strong and stiff. We can make things that are very, very durable, things like, say, Teflon that we coat our frying pans with. We can either make polymers that are either flammable, or probably more likely we can add things to them to limit their flammability so that they're less likely to catch fire, although generally most polymers tend to be reasonably flammable. And we can also add things to them to make them, for example, UV resistant. So if they're out in the sun for large amounts of time, they're not going to degrade or break down. The disadvantages, they're not biodegradable, is the biggest and most serious problem with most polymers. Not all, but most. We'll come back to this a bit later on. They will persist in the environment and can harm wildlife. So that's the classic, the turtle with the ring pull, not the ring pull, with the plastic can holder stuck around its neck, or you've probably seen all of those images. The other problem with polymers is that they, as I said before, they tend to be quite flammable. So they will tend to burn or combust, as we say now in science. And the decomposition, or the combustion or the decomposition of the polymers can release toxic chemicals into the environment. They are, to me, if you know those advantages and disadvantages, you should be fine. You're probably not going to need to remember all of those, and hopefully a lot of those sort of link in with other things we've done in the course and are just common sense. We need to compare the effects of heating on thermoplastic and thermoset polymers. So thermoplastic polymers soften when heated, they're moldable, and then they harden again when they're cooled. So if you've ever built something in design and tech out of acrylic, where you sort of heat it up and then bend it into like a cake slice or something like that, and then once it goes cold it sets again, that's the idea of a thermoplastic. We can heat it up, mold it, melt it, bend it, and then when it cools down it'll be set in that shape. Thermoset plastics don't soften on heating. They'll often catch fire before they'll melt, or they'll start to decompose. So that's the difference between a thermoplastic and a thermoset. Thermoplastic soften when heated, thermoset won't soften when heated. And we're going to explore in a little sec about why we might see those different properties. So organic polymers can have different properties such as rigidity, depending on the monomers and the degree of cross-linking between the chain. Compare the physical properties of polymers with different degrees of cross-linking and secondary interactions between the chain. So we can all imagine here in our diagram that we've got some continuous chain in our polymer, whether that's an addition polymer like PVC, or whether it's a polyester or a polyamide, a condensation polymer. Now generally, if we just have all of these long, thin lines and we don't have strong or much interactions between the chains, then we're going to get quite soft plastics, quite low melting points, probably be thermoplastic, as I just said before, will probably be more easy to recycle because they can be melted down and remolded. So when you get these types of chains, we talk about weak crosslinks. So the crosslinks, if you like, they would only be in the case of the weak ones, dispersion forces or dipole-dipole or even hydrogen bonds. So all of your secondary bonds or your secondary interactions, they, if you like, aren't permanent crosslinks, so they can sort of be broken and then remade, or they won't be very strong. That's why we can bend these things and melt them. However, if you get really strong, if you get strong crosslinks, so crosslinks that are built from covalent bonds, ionic bonds, so our primary bonds, then these polymers tend to be much stronger. They'll be much more rigid. They'll have higher melting points. They'll be more difficult to recycle because of the higher melting points, and therefore they're more likely to be thermoset plastics. So hopefully that sort of makes sense. I think most people find that bit not too complex or too difficult to understand, but if you're not sure about that, please do ask. Let's keep moving. Okay, in this next part and the final part on polymers, we're going to really get into some of the environmental aspects of using polymers. So the first thing we need to be able to do is discuss the advantages and disadvantages of making polymers from fossil resources or from renewable materials. So when we say fossil resources, we basically mean fossil fuels. When we say renewable materials, we tend to mean what we call biomass, so stuff that's either grown from, well, generally is grown from plants or is the waste from growing other crops and that sort of thing. So, what's the advantages of fossil fuels? They're relatively abundant at present, and there's a very well-established industry to basically mine the crude oil and refine that crude oil and give us all the starting materials we need to make lots and lots of polymers. There is a large variety of polymers that can be produced from these fossil fuels. So, you know, we can make lots and lots of different polymers from the fossil fuels. The disadvantages, obviously, of making the fossil fuels goes back to some stuff that we've talked about earlier. They're a non-renewable resource. At some point, we are going to run out of crude oil and those supplies. So, you know, it's a finite resource. We're using it up. So, again, using it for plastic, to make plastic, or to use it for fuel is all using it up, and it won't be there forever. So that takes us to building polymers out of biomass, which is, for the most part, we're talking here about plant material. These are a renewable source, so we can grow more and more plants to make more and more polymers, so that's an advantage. And in many cases, we can use parts of plant that would currently be waste, so stuff that might be discarded either when we're producing a food crop or a timber crop or something like that. We can take that waste and actually use it as the starting material to build polymers, rather than just basically sending it to waste. However, the disadvantage of the biomass is there's quite a limited range of polymers that can be produced at the present. We can't build anywhere near as many polymers from biomass as we can from fossil fuels. And the other thing is, if we start to use biomass more and more to make this the starting material for polymers, that's more likely to compete you're more likely to have competition for land use with things like food production. So then, you know, do we use the land to grow food to eat, or do we use the land to grow crops to make polymers? And those two things can compete with each other, and there can be problems with that. So, finally, we need to explain why some polymers are biodegradable but others are not, and then also to talk about and explain the advantages of polymers being biodegradable. The second part I think is fairly obvious, but we'll go through it anyway, but let's talk about that first part. The addition polymers, so they're the ones made from the alkenes with the continuous backbone of carbon atoms, tend not to be biodegradable. This is due to the continuous network of carbon-carbon bonds in the backbone of the polymer. So examples like PVC that I talked about earlier tend to not be biodegradable because those carbon-carbon bonds are quite strong, quite difficult to break. There isn't anything in nature that will easily break those bonds down. However, condensation polymers tend to be biodegradable. Not completely, but they're more likely to be biodegradable. That's what I mean by tend. They contain carbon-oxygen and carbon-nitrogen bonds, and these can be broken down in nature by either enzymes in the soil. So basically little microorganisms that live in the soil will often have the ability to break down the carbon-oxygen and the carbon-nitrogen bonds, but not so much the carbon-carbon bonds. And we can also get photodegradation from absorbing light. So when carbon-oxygen bonds in particular absorb light, they can be broken, and this can help to break down that structure of the polymer. So it's also why, you know, something made of, say, polyester is more likely to degrade if it's left in the sun and go, say, brittle, than maybe, say, a piece of PVC, which is much more resistant to that UV in particular light or from absorbing light. Biodegradable polymers will not persist in the environment and damage wildlife. So that's the final point there. That's the advantage of the biodegradable polymers, is because they break down, less likely to have environmental impacts. So that completes the story of polymers. The next video we will look at part B of the materials topic, which is metals. Cheers.